First, let's have a look at the relationship between resistivity and the temperature. So generally, when we increase the temperature in metals, its resistivity increases. Likewise, when the temperature of metals drops, their resistivity decreases. The stage at which the temperature is lowered to the point where the metal resistivity is brought close to zero is what you call a superconductivity. So that's a general idea about the temperature resistivity relationship. So in order to produce current flow, all the electrons have to move in one direction. Contrastingly, if the electrons flow randomly in a different direction, electricity is not be formed. On a microscopic level, when we increase the temperature of a metal, the atoms in it vibrate as they vibrate. Collision between electrons occur, resulting in the random motion of electrons in the metals, which results in increase in the resistivity, thus hampering the current flow in the given metal. Likewise, when we decrease the temperature of the metal, the vibration of atoms is minimal, hence collision of electron is low, which results in a drop in resistivity. Thus, the flow of current is higher. So we can tell one of the variables that affect electrical resistance is temperature. There are few other variables that affect resistivity of the metal. One of the variable is the length of the metal. Let's take two metal rods of the same material, as in they got the same resistivity with the same area but differing length. One is longer rod than the other. So here the current has to flow through the entire length of the metal rod. It's pretty obvious that the longer rod is going to experience more resistivity than the shorter one, since the electrons are going to experience more collision over the longer rod. Hence, we can say as the length increases, resistivity increases. Next variable is the area of the metal. We got a metal of the same material, same length but differing area. One with a wider area while the other with narrower area. The wider metal will have a great cross-sectional area, while the narrower metal will have the less area. The narrower the area, the more the collision, hence the resistivity increases. The wider the area, the more spacious for charges to flow, hence lesser resistance. Hence we can say as the area increases, resistivity decreases. Another variable that affects the electrical resistivity is the material the metal or wire is made of. There are various materials out there and each got their own differing conducting ability. The conducting ability of a material is often indicated by the resistivity of the material. There is a broad range of resistivity values for each material. Materials with lower resistivities offer less resistance to the flow of charge. In other words, they are better conductors. Material with high resistivity shows high resistance to the flow of charge and their conducting abilities drop. So we can write R equal to Rho L over A, where the constant Rho depends on the nature of the material, which is the resistivity value we just talked about. It is the specific resistivity of the material. The specific resistivity of the material depends on its temperature. So if Rho naught and Rho theta are the values of resistivity of the material at 0 degrees Celsius and theta degrees Celsius, then over a temperature range we have Rho theta equal to Rho naught bracket 1 plus alpha theta close bracket, where alpha is the temperature coefficient of resistivity of the material. Consequently, for resistance, we can write it is R theta equal to R naught into the bracket 1 plus alpha theta. Here in this question, R theta is 115 ohm, R naught is 50 ohm at 0 degrees Celsius, alpha is 4.0 into 10 to the power of minus 3 degrees Celsius minus 1. When we make theta as the subject, the equation will be rearranged as follows. Now when we substitute the given values, we'd be getting the answer, and that is 325 degrees Celsius.